All right, today let's look at how to do cohesive elements or cohesive material models inside Ansys LS-Dyna. So what I have here is a video of essentially almost like a double cantilever peel test, where we're just peeling the bond away from one part to another, and then you can sort of see the element gets deleted. And I'll talk about the logic of how this happens and how to set a model like this up. Okay, so before I get into the actual demo, which is I'm gonna do a problem like this. This is basically these two blocks right here are like the load applicator, right? And then this is the top P substrate, bottom P substrate, and this right here is a layer of the cohesive elements, which is gonna bond the piece together. Now, before I talk about uh, uh, how to set this up in the GUI, right? It is useful to think about the basic logic behind a cohesive element, right? So, you know, when we talk about cohesive elements, this is not the same as any other finite element, right? Where we're sort of calculating the stress and strain from the displacements and the velocity of the nodes, right? We're mostly looking at something called attraction separation functions. So basically, a single element, the behavior of a single cohesive element essentially follows this traction separation function, right? So basically, it starts at nothing, right? As you put a load on the cohesive element, it's going to behave elastically until it reaches a tip point. This point right here is where the damage initiation starts, right? So when damage initiation starts, you are going to keep increasing the separation distance, right? Imagine the element gets bigger and bigger and bigger. And then as damage initiation starts, if you were to unload it, you are going to permanently lose some. You're going to permanently lose some, change the stiffness of it because you're damaging the element itself, right? And then if you keep loading it, keep loading it, eventually it reaches this maximum separation distance, at which point element gets deleted, right? And that's in essence what a cohesive element is, right? It's calculating essentially like a force versus separation type of behavior, as opposed to really calculating like stress and strain. That's really, even though you can probe that, what it's really doing is to model the damage initiations, and in some cases the evolution as well, right? Now, this thing so LS-Dyna has a lot of different options, right, for modeling cohesive element. I listed out 5 of them, and there's maybe a couple more in here that I haven't listed, right? So we're gonna talk about 138, 186, and 240 because I have some data that I can use to sort of demonstrate. But I think I'm just only gonna show the post processing for 138 because the setup is very similar. Now, the key thing to know about cohesive element is that there are two different element formulations, right? One is 19 for connecting solids, the other is 20 for connecting shells. So if you didn't know this, shell element has 6 degrees of freedom, whereas solid element has 3. So that's why we need a different element formulation to sort of account for the moments, for the rotations of the shell element nodes. And then we're gonna use element 19 in the example problem that I'm about to demonstrate. Okay. All right, let's do the problem together. What we have here, I'm just gonna go down the basic setup. There's a couple different things I would need to do, right? I'm gonna open up all the tree. First thing I'm gonna do is I'm gonna suppress this because I don't need it. These parts are shared topology, which means some of the nodes are shared together. I didn't show that step, but you can sort of imagine this is why I'm not creating any kind of tight contact. Usually you have to do that if you needed to, but in this case I already no merged these in the geometry prep step. Okay, and what I'm gonna do next is that um, I'm going to first define these four materials. What they are really doesn't matter. I think I'm just gonna leave them as structural steel. This is basically 200 gigapascal steel. For this component, I'm gonna call this component the CZM part, right? And then I'm gonna add a material model to it. Well, in fact, I'm gonna add 3 different material model to it because in this case, because I have 3 different material model I want to test. What I can do is actually write out 3 different input file separately as I do this, right? So the first thing I'm gonna do is I'm going to input mat sorry, I'm trying to input mat 138, and then mat 186, and then mat 240. Okay, but I'm only going to run one of them, but I'm going to set up all of them because it's very easy to include multiple materials in Dyna in this workbench environment. So for mat 136, this is the card I'm going to be using. I'll talk about the card later. This is a dummy material card that I created. The actual number itself, really, like, we're not, because I'm just using this as sort of as a way to demonstrate, right? I'm just gonna use some dummy material model. Oh, did I put it in the 240 side? Oops, sorry. This actually goes into the 136 snippet, 138 snippet. All right, for 186, I'm going to copy 186 as well. And for 240, I'm going to copy 240. And I'm gonna show why I'm doing this later, right? But for now, I'm just gonna suppress these two. Because I want the first input file I'm gonna create is for my 138, but I can assign different material very easily inside Workbench Dyna. Okay. Now for meshing, for something like this, I could be more intelligent with meshing, but for the sake of time, right, I'm just gonna brick the whole thing with a relatively small element size and just mesh it. It should turn out okay. Sometimes we'll wanna modify the element size of the cohesive element because it's a very small, thin layer. In this case, the layer is not that thin. I made it arbitrarily larger, but sometimes it will have to control the element size on this component, and that could create issues if it's too small. But in this case, I just put a whole brick on everything. It's a pretty clean mesh for the purpose of demonstrations. All right, now what comes next is that let's set up the basic constraints first, right? So what I kind of want to do for something like this, right? I'm not really following the actual, like, the cantilever beam tests from the standard, right? I'm just gonna do sort of an arbitrary constraint. But basically, what I want to do is that I don't really want a bottom piece to move, right? So I'm just gonna fix these two pieces, and then I'm also going to sort of fix these two sides as well. Because I just want a PO action to occur, which is why I'm just fixing all four sides. I think this doesn't exactly follow the standard, but for the sake of demonstration, this is fine. I don't think it matters. In the case here, what I'm also going to do is that I'm going to use these two plates as my load applicator. So I'm going to apply the displacement on this component, and then what I want to do here is to sort of move this plate upwards, right? So what I want to do here is, let's set a termination time first. Let's set a termination time to 4.5 seconds. So I'm gonna move this thing in the negative x direction by 4.5 seconds by 3.75 millimeters. Oops. Oh, oops. Negative 3.75 millimeters. Right. So this thing is gonna go up by 3.75 millimeters. Excuse me, yeah, by 3.75 millimeters. Oh, actually, I'm sorry, that's not what I want to do. This number is actually off. I was looking at the wrong thing. So let's just move this a little bit more. Let's just move this by 50 to follow, because in this example I already created, I actually used 50. I just got the number wrong. Sorry about that. All right, so I'm gonna use negative 50 to push this upwards, right? And I have a fixed support. So this basically establishes the whole thing, and I'm gonna do this over 1 second instead of 4.5 seconds. So let's just do this by negative 50, and I'll delete this line. Okay, and this low curve is going to push this thing upwards, and it's fixed on the other end, and I have a 1 second duration. For the units, I'm gonna use Newton millimeter, and then that's the basic low setup. Now, what I want to do next is to define the behavior or some of the situation with the cohesive elements, right? So first of all, for my 186, this TSL2 and TSL1, or the TSL, these low curve 111 and 222, these two low curve defines the traction separation function in the two different directions. So what we want to do here is actually include the low curve. And the low curve I have, I'm going to be using are basically these two. Right, so 111, 222, and then this right here gives you the basic, low traction separation function for the two low curve we're using. The reason why I'm using low curve is that my 186 is a nonlinear traction separation, whereas 138 is a linear traction separations. Which is why we're using a low curve to define that. My 186 is very useful. It usually fits very well with experimental data if you ever play with stuff like this. LS-LCID. Alright, that's the first I'm gonna do. But remember, I'm not outputting my 186, so I'm gonna suppress it because I won't use it. Um, yeah, I have these two. Good. All right, and then what I'm gonna do next is that I'm going to sort of define the section for these four solid elements. So usually what we want these two to do is that we don't really want to use one. We don't really want to use a. Well, I guess in this case it's okay for me to use the 1-point co-rotational. Sometimes you could use a different element formulation, but in this case I just define the section this way. And what I'm gonna do next is to define the section for this part. I'm gonna actually isolate it. Okay, so this is essentially the cohesive element area, right? Now remember, if you remember what I said earlier, is that for cohesive element, the section has to be a outform 19 and outform 20. Now if you use this section functionality in Workbench Dyna, you realize that 19 and 20 doesn't exist here, right? Then none of this is outform 19 or outform 20. So what we want to do is to actually use the keyword manager, which I believe is right here. Let me just put this in the. Yeah, it's a little bit outside my window, unfortunately. Let's put it here for now. So what I want to do here is that let's do a section card, section solid, because these are solid elements. All right, I give you a bunch of information, but whatever. I'm trying to pin it correctly. All right, I'm gonna add it. Now, okay, the section solid here it gets added. Let me dock this a little bit better so everybody can see it. It's a little bit awkward. Sorry about that. All right, so this add button right here is what allows me to add the section solid. And what I want to do here is to essentially now go down to 19, which I believe is, if I can find it, the cohesive element formulations. Where is it? Right there. And if you want to tell what it is, right, so you can see 19 here is a noted 4-point cohesive element, 0 mark 1 to 6. They basically copy this directly from the documentation, which is why I don't usually use the keyword manager. I feel like it's really silly. I would rather run my own card. But in this case, it's a good way to demonstrate it. And what I can also do is that this allows me to directly assign a section card to a component that I'm not able to do with this section button right here, right? And then what I want to do next is, so in addition to section, I want to create a part card, right? Even though the part card is already created up here, it's a little weird with this. What we want to do here is that this part card has to be scoped to the component of interest, which is this one, right? And then it's going to, we're not using the thermal card, so not used. And then the hourglass, we're going to not use. And then the equation of state, we don't really need that. Actually, sorry. Yeah, not used. Now for the material, right? If we choose structural steel, it's clearly incorrect. What we want to do is to choose program controlled. What happens with the program controlled is that whatever I'm putting down in here is going to be utilized by program controlled. Don't ask me why that is. That's just the way the preprocessor currently works. It's a little bit strange. For the section card, I'm gonna choose the section solid card right there, right? And the heading is just the part I'm calling the CZM part, and unit system in Newton millimeters. Okay, Now, what these two things do is that you assign a section solid with alpha 19 to this component, right? Which is sort of what we wanted to do, right? Uh, and that's what was accomplished by these two keyword manager items. Okay. And the last thing I want to do is I'm going to add a database card, and this database card is going to basically I always use my own D3 plot, so I'm just gonna put this here and then put this like to like a native to like 3, and then I should be good to go. Okay, now I'm gonna write out 3 different input files, right? This is why I have 3 different material cards here. Because I want to actually test out all 3 different material. Even though in the video I may not show all of it, right? So what I want to do here is that I'm gonna call this a demo, and then I'm gonna put this as mat demo mat 138. Okay, that's mat 138. Now for 186, that's what I'm doing. I'm just unsuppress and suppress, and then unsuppress low curve ID, and then write out mount 186. And then for the 240, I'm going to suppress, unsuppress, and then suppress, and then write out another file. 240. Okay. And that right there concludes the basic demonstration for the model, right? And then obviously I'm now, for the sake of time, I'm not gonna show all the results, right? This right here is the mat 138 results. Now if you see what's happening here is that I have changed the scale of my displacement to here. So anything that's a red color, quote unquote, is above 7.47 millimeter in displacement, right? In a vertical displacement. Now if you look at if you look at this parameter right here, you see the 7498, this UND, and UTD, right? These are basically the ultimate displacement in normal and in shear that's allowed by this cohesive zone model. So because of that, right, if we look at LS Pose again, you can see the elements start to get deleted. Like if I zoom in a little bit, right? Oh, I can't really see this. Just a graphics issue. You see, as soon as it gets to about the red color, right, the elements start to get deleted, because that's when it reaches the ultimate displacement. And that, in essence, is what's happening in this traction separation function, right? As soon as it reaches here, element gets deleted. But the actual behavior is that you have a linear elastic behavior to start until you reach damage initiations. Then it softens, right, until it reaches the maximum separation distance, and then the element gets deleted. So that's essentially what it's doing to model this cohesive zone material. Now, if we dig a little bit deeper into the 3 different material models that we looked at, right? One is 138. Now I have a little bit of information here. If you want to pause the video, you can look at it. But this basically came directly from the documentations. The key thing to know here is that the 138 is a mixed mode cohesive zone model, but it's related to a linear softening. So as you can see, it very much matches this kind of behavior, right? The key thing to sort of know, right, these are the ultimate distance that you can define, right? It's sort of looking at the relationship between the traction, which are sort of defined as the E and the ET parameter here. It's a really weird unit. It's a unit of stress divided by length, right? Because it's sort of scaled to the cohesive element size. And then the peak traction right here, these two are essentially the location where the maximum place where damage initiation will occur, and then these two right here is the area under the curve, which is essentially your fracture energy or energy release. And then if you look at the actual behavior, you have on one side you have mode 1, which is in normal, mode 2, which is in shear, and in mixed mode has an exponent component, which is this which I believe is this XMU parameter, right? This XMU parameter basically defines where this this green curve will land, which is a mix of the normal and shear component relationship, right? So you're looking at the actual traction separation function somewhere in the middle of your normal and your shear behaviors, right? So this is a very very well made uh, 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 sort of image to describe how this works. Now, if you look at 186, right, the biggest difference between 138 and 186 is that 186 is a nonlinear traction separation functions, right? So basically look like this. Uh, Everything else is very, very similar to what we're looking at. So there's not much else to talk about. You can read through these. I put this in here mostly for myself, all right, because I like to create a package where I can go back and look at it later. Now for 240, right, this is the one where it has a lot of stuff. I found a paper from Dynamore that describe essentially a study that was done, and then material model they use is essentially outlined here. This is a MAT 240 material model, which is what I'm using in my demonstrations, right? In this study, they basically tested a different cohesive element against different kind of substrate, solid element, shell element, has gap in the shell, no gap in the shell, and so on and so forth. So it's a good way to test out the capability of the cohesive elements. But the MAT 240 is a very useful uh, uh, material model because it allows you to do a lot more things than the other two, right? So it does give you ability to consider plasticity, consider rate dependency, consider temperature dependency, right? Because there are parameter in here that lets you account for those. He also give you the option to use a power law to define damage evolutions, right? So you can sort of see the actual curve that's used in MAT 240 follows something that looks like this. It's still a mixed mode relationship with a normal and a shear component and a coefficient that defines the combination of the two, the mixed mode of the two, right? But it gives you the ability to account for rate effects, temperature effects, which is very much like what's happening in reality. Because in reality, a lot of the material that we're modeling with cohesive elements are in fact rate dependent and temperature dependent. I have no idea how one tests for these, but I know the capability exists in the code, which is why I definitely want to present it. Okay, thank you very much. Hopefully this is helpful to you guys.